All right, hi guys. So today we are looking at this P5 on popular request because for P4 you guys have the recordings anyways, and P5 is something you guys wanted me to go over. So with P5 we are going over like the most recent papers which are available here. So we're starting with summer 23, paper 52. And because of the shortage of time, and because you guys are also having like a lot of papers in a few days, so I'm not giving any homework for this one. So there's summer 23, paper 52, which we're doing today. And there's going to be winter 23, paper 52, which we'll be doing the day after. And on 12th May, we will be having our AMA session in which I'll also be disclosing a guest paper, and we'll be looking over some of the questions and just going through all of the syllabus at a glance and doing some quick revision. So let's get started with this paper today. Again, with P5s, there is no such thing as a certain paper being more difficult, some paper being really easy. It really doesn't work like that. All P5s are like of an equal difficulty. There is no such thing that a certain P5 being harder or easier than another one. So let's start with question number 1. Two coils P and Q are placed close to each other as is shown. A resistor of resistance R is connected in series with coil P. A changing magnetic flux of frequency F in coil P causes an EMF to be induced across the terminals of coil Q. It is suggested that E is related to R by this relationship. So E is the induced EMF, 2 pi F M V over R plus K. V is the potential difference. V is the potential difference across resistor and coil P, and K and M are constants. Plan a lab experiment to test the relationship between E and R. Right? So E is the induced EMF and R is the resistance. Now, just up till now, you can figure out the definition of your problem, which is that what is the dependent variable, what is the independent variable, what's the what do you call it, what's the control variables as well, right? So you can see here that we would be changing the resistances R, and we would be measuring the EMF E. So let's first write this. So we vary R and measure E, the induced EMF. Again, a very easy way to see what the control variables are. Most of the times this will work. Sometimes you will need to think about something else as well. But most of the times this approach works is that here you are investigating the relationship between E and R. K and M are constants. So K and M are constants. So then you can see that whatever is not your primary variables, or whatever is not your independent dependent variables, and what is also not your constants, these can be your control variables, right? So here I can see that F and V are my control variables. So these two I can get just from the equation. But also, if you think about it, and if you think about all the magnetism you studied, you also know that magnetic flux density basically falls off with distance, right? The magnetic flux density in this coil, when it's going to be cut by this coil, that is what is going to cause an induced EMF. So by the way, we can also say that both of these coils, their distance should also be the same. Their separation, that should also be the same. So now for the control variables, I'll say this, that keep V, F, and distance between the coils as constant. Again, I'm pretty sure that nobody, at least the ones who are watching this, nobody makes this rookie mistake that you say control these variables. We say that these are supposed to be kept constant, right? So now that we have defined our, what do you call it? Now that we have defined our problem, now it's time for us to go on to the circuit diagram. So what I'll do is that I'll just take a screenshot of this to work with. I'll be adding on to this diagram. Again, this is a electrical circuit, as you guys can obviously see. So in electrical circuits, the examiner is not as concerned with this entire thing floating in air. Because if you think about all the electrical circuits you've made in your entire life, the idea is that for all the electrical circuits, you've never talked about whether this is kept on a bench or if it's kept on, if it's hung by some stand, because that's not really a relevant detail here, right? So what we'll do is we can just make this still float in air because this is a electrical circuit. So let's have this here now. So this is my circuit as was there. And now, because I know that coil P, if I look at this above, there was a changing magnetic flux of frequency F in coil P, right? So changing magnetic flux of frequency in coil P, you know how this is going to work is that if I have an AC power supply connected across coil P, right? A alternating current will give rise to an alternating magnetic flux as well. So first off, there needs to be an alternating supply here. So I draw this alternating supply. This is the circuit symbol for it. You should additionally also label that this is your alternating voltage or current supply. Again, also some mistakes that a lot of people do make while drawing the diagram is that even though they make good diagrams, they do not do labeling at all. If something has been explicitly labeled by the examiner, please label it again. A lot of the times there are marks just for labeling all of this very clearly. So label should be really clear, right? So I've labeled this R again, I've labeled P again, I've labeled Q again, and anything new that I'm basically having here, that will also be labeled, right? So this is my alternating voltage supply, which is going to cause that EMF, that changing magnetic flux. And then what else do I need? So with the power supply, if I look up here, so I also need a changing magnetic flux of frequency F. So that is done, causes an EMF E to be induced across terminals of Q. It is suggested that E is related to R by the relationship. So for E, obviously, because this is also going to be a varying EMF. So for this, a normal voltmeter would not work. And you guys know that for this one, I should have a oscilloscope here. Again, if you guys have been watching my YouTube channel, so I just recently did a video on the most recent P5, which is out there right now, which is March 24. And that also had a case where we had to talk about an oscilloscope. If you do have a question which is on oscilloscopes, I think you're pretty much in luck because with oscilloscopes, you can score some really easy additional detail marks. So this is the circuit symbol. If you don't know it, again, not a problem as long as you label this clearly. So this is the oscilloscope, right? What else would we be needing? So we have the AC supply and yeah. So the frequency changing magnetic flux of frequency F in coil P causes an EMF to be induced across terminals of Q. Suggested E and R is related by this relationship. So V is potential difference across the resistor, coil P, K, and M. So because we'll also be needing the potential difference across the resistor, so I think we should also have a voltmeter in parallel, right? So let's also add that, a voltmeter in parallel with the resistor. Again, you know how the voltmeter is supposed to be connected is in parallel. So we just make this. And even though this is pretty self-explanatory, I'm still going to label this as the voltmeter. Right, so I think everything we need now is written. Also, here we were not told, and again, if you have done a lot of practice, you might remember seeing this, that sometimes you see that there are many different resistances available. That is sometimes written. Here, you did not see this written anywhere. This means that probably these resistances are unmarked. So in your experimental method, you should also in some way state how you are going to find the resistance of these resistors are, right? So you can also just talk about a simple ohm meter method. That is probably the easiest one to say. Or you can also talk about a voltmeter and a current method, where for all of these resistors, you take the voltage across it, the current through it, and you use R equals V over I. But I'll be talking about the ohm meter because that is more time efficient to write. You get the same marks for saying either this or this. So measuring R using an ohm meter just makes more sense, right? So now that I have decided what this circuit diagram looks like, now I'll be talking about how to measure each and everything here. So first off, let's see. So we have E, R, F, and V, right? So for V, I'll say this as is very obvious. So measure V from the voltmeter as shown. Now, if you remember here, this V was our control variable, right? V is supposed to not change, by the way. So if you think about V, here there is no such way to talk about how to keep V constant, right? Otherwise, you'll have to use an variable resistor, and life is hard enough as it is without it here. So let's just not talk about that, which is how you talk about V, right? Because usually for the control variables, we should talk about how it should be constant. But here it's a bit difficult to do that. So let's keep that on the side for now, and then we'll come back to it later. So right now we just say we measure V from the voltmeter as shown. For the frequency, obviously now this is going to come from the oscilloscope. I can write a lot about this. So for the oscilloscope, you can obviously talk about the time-based setting. So multiply the time base by the horizontal divisions in which one wave forms. To get the time period. And then you can talk about the frequency f being equal to 1 over the time period. Right, so this is nice about oscilloscopes, that you get some additional detail marks really easily here. All right. So also about the induced EMF E, which is what we have to measure here. You can also talk about that with respect to the Y gain, right? Because V we have measured from the voltmeter, but now I'm talking about E, the induced EMF. So you'll say similarly, multiply the Y gain by vertical divisions to find E, right? So this is done as well. What else? What else can we talk about here is, so we've talked about E, we've talked about V, we've talked about F. Also, whenever you do have a question on how you, when you say that something should be kept constant, it's also nice for you to think about how this certain control variable can be kept constant, as you were thinking about the voltmeter for now, right? So for the voltage from the voltmeter, again, this in a way here, it would be kept constant if we always basically tune this voltage supply, if we have a varying supply. So if we change the voltage reading so that it always gives us the same voltmeter reading, this is also something we could have talked about. But right now I want to talk about this thing here, the distance between the two coils being constant. How can we talk about that? So we can say that if we have some way of clamping the coils, right? So if we have some way of clamping the coils, we can say that this would enable the distance to be constant. So for example, if I take up, let's say I introduce some clamps into here. These are my clamps. Again, it's totally fine that you like identify the different things here while you're writing the experimental procedure. So you guys should just have enough space in your diagrams that you can add on to it. So I'll say clamp the coils to keep the distance constant. All right, so do keep this in mind that whenever you are talking about keeping some variable constant, most of the times you can get marks for talking about how you keep them constant. So to keep the distance between coils constant. Also, I hope nobody's under this delusion that just because additional detail appears in the mark scheme in the end, you have to write it in the end. That's not at all how it goes. How I prefer to do it is I tend to write it along with my experimental procedure so that I do not forget it. And yeah, so towards the end of the experiment, I just write the safety precaution stuff. So this is what I have written now. So I've talked about V, I've talked about F, I've talked about E, I've talked about R. So I think everything is done here, right? Now at this point, it's also useful for you to think about if we can do anything here for averaging, but really we can't, right? This is not a case where averaging would be really easy to do. So something else we can think about, and this is also like a sort of a guideline that you want to have. This is also things you want to think about, is that you want your dependent variable to be as large as possible, right? To reduce uncertainty, you want your dependent variable to be as large as possible. So how can we find a E which is as large as possible? So there are some couple of ways to do this. Is that if you also have many turns on the wire, or if you use a really large voltage supply, so this can cause your E to be larger, and this will reduce the percentage uncertainty in it. So E can be made larger by increasing your current or voltage, or you can also say the turns on the coil, and this will reduce its percentage uncertainty. So I think this is like a lot of stuff on the additional detail part. Now let's get started with the graph and what must be plotted against what. So this is the equation that we had. Again, let's capture this as well. So this was done. So this is the equation that we have here now. So if you think about this, we have E as an independent variable, and there's the R, which is a dependent variable. So if I just expand out these brackets, I think that's going to work in my favor. So if I write it like this, that this is 2 pi fm v over r plus k, right? And now I basically need to have r separate in some way. So what should I do here is if I cross multiply, so I can get something of use here. Basically, if I have this, that if I cross multiply r, so this becomes 2 pi fm v over e. And if I do this, that if I write it like this, r equals 1. So r equals, let me write it like this, just so this is more visible. So I just separate the e from this because I know it's going to be, it's like one of my primary variables. One is r, one is e. So I just want to have it separate. So this is 2 pi fm v, and I subtract the k on the other side. There is no such hard and fast rule on what you want on your y-axis, what you want on your x-axis. It works both ways. So what I'm thinking now is that I can have this on my y, this on my x, and then whatever is my x, all of this is my gradient, all of this is my y-intercept, right? So I just leave out some space here, and first I write plot r versus 1 over e, right? So r is on my y-axis and 1 over e is on the x-axis. And I write this classic line, which always helps you score marks. So this relationship is valid if the graph is a straight line. Here, would it pass through the origin? The answer to that question is no, it would not, because you do have a y-intercept here, which is really this value, right? Other times when you do not have a y-intercept, you do need to say that it passes through the origin. So here you would not say this because it does have a y-intercept. Now, at this point, you should now also understand that just saying what your gradient or what your y-intercept is equal to is not sufficient. The constants that you need to find must be made subjects of those equations. So for example, if I look at my gradient here, so the gradient is 2 pi fmv. Just saying this is not good enough. You should make what you want the subject of this equation. If I remember correctly, m is the constant I wanted to find. So I should make m the subject here. So m is gradient over 2 pi fv, right? Similarly, for the y-intercept, I can see that the y-intercept is minus k, but I should make k the subject. So if y-intercept is minus k, this means that k is negative of the y-intercept. If you do not do this step, you will lose marks. Even if your expressions for the gradient or your expressions for the y-intercept are correct, if you do not do this, you will lose marks. All right. So now that we're done with like all of this experimental process, this is where I now start to think about the safety procedures. So safety precautions, you have a maximum of 1 mark that you can gain here. So for the safety precautions, this is one which deals with electricity, and also with electricity, it deals with coils and some of these components. So what you should have done here, what we've not done here, but what we should have done is to have just a small switch over here. But even if you do not if you do not draw the switch here explicitly, and if you still say this in your safety precaution, you can get marks, is that you should switch off the circuit when it's not in use to avoid the coil getting too hot, right? Or you can also say that you use rubber gloves to prevent burns from this. So these are like some of the most obvious ones. Or similarly, because of electricity, you can also talk about the use of insulating gloves to prevent against electric shocks, right? At max, you have just 1 mark for safety precautions. So don't overdo this. So just say that use rubber gloves to protect against burns from the hot coil. All right. Any question up till now? Anything related to question number 1 that you guys want me to go over? Otherwise, we'll move on to 2. All right. So now we have question number 2. Student investigates how the volume of a gas varies with the temperature. What I usually do, and I find that this is the most time efficient approach, is that I just start reading the question from here. And then I come back to the rest of the question when I actually reach those last parts, because that's where it's really useful, right? So it is suggested that V and theta are related by this equation, PV equals to YK theta plus Z, K is Boltzmann, all of this stuff. Graph is plotted of V on the y-axis against theta on the x-axis. Determine expressions for the gradient and the y-intercept. If V is on my y-axis, let's first isolate this. So V would be yk theta over P plus ykz over P, right? So this is what I have on my y. This is what I have on my x. So all of this is the gradient. All of this is the y-intercept. So for the gradient, yk over P. For the y-intercept, ykz over P, right? Now, as you guys know, the next step will be to fill out this table. So the value of D is 27.9 plus or minus 0.1 millimeters. Volume is calculated using pi d square h over 4. Calculate and record values of V, which is going to be in 10 to the negative 5 meter cube in table 2.1. Include the absolute uncertainties in V. Now for the absolute uncertainties, you have the formula method and you have the Maxwell method. I tend to use the Maxwell method only when you have no formula at all, or if it's really difficult to find it out. For example, in the case of a log one, where you do not have a formula that you know how to use for logs. So you just use the Maxwell then, but in almost every other case, I do use the formula. So for V, I can see here that the percentage uncertainty in V would be twice the percentage uncertainty in D plus the percentage uncertainty in H, right? The value of D is always this thing. So I can find out 1% uncertainty and I can keep on using this always. So 0.1 over 27.9 times 100. This turns out to be 0.358%. And because it's twice, so multiply this by 2 as well. So this turns out to be 0.717% plus whatever percentage uncertainty of H I'll be getting in each part. That is going to be my percentage uncertainty in V. And once I have all of these principal values, I can multiply by them and find out the absolute uncertainty, right? So let's look here now. So let's first find out all the principal values. Value of D is this, value of H is this. I need to use this formula. So let's go ahead and do this. So pi, there is D square. So 27.9 into 10 to the negative 3 squared. H is 62.4. This is also millimeters into 10 to the negative 3. No square on this, divided by 4. So this value turns out to be 3.814. Again, you have these two things which were used. There was this value, which is 3SF. These values, which are also 3SF. So your choice is either 3 or 4 SF. But always, to make your plotting easier, take the less number of SFs. So instead of 4, I'll just be doing this with 3. It does make plotting really easy. So 3.814 turns into 3.81, right? And now I do this for all of the other values in the same way. It also often helps that to do this quickly, you have this formula set up on your calculator, and then you just go into a older formula, you just change up the values, and you get the new values then, right? It's one of the easier ways to save some time on this part. Only thing that I now have to do is, instead of 62.4, I substitute 65.2. Turns out to be 3.986, so 3.99. Similarly, now I have to do this for 68.1. So 4.163, so 4.16. Now 70.9. So 4.334, so 4.33, then 73.3. 4.481, so 4.48. And then the last one is 76.1. This turns out to be 4.652, so 4.65. Now that I have all of these values, now I can find out the percentage uncertainties for each of these cases. So 0.1 over 62.4 times 100 is 0.16%. I add to this 0.16%, I add this value, and then I take that percentage of this thing, right? I'm doing this all on my calculator. So 0.16 plus 0.717, and I take this percentage of 3.81. So this turns out to be 0.033. So 0.033. If I look at the number of significant figures here, 0.033. So this would be 0.03, right? 1 SF absolute uncertainty. 3.99, again, 0.1 over 65.2 times 100. This here turns out to be 0.153%. I add to this 0.717. I take this percentage of 3.99. Turns out to be 0.034 as well. 0.03 plus minus 0.1 over 68.1 into 100 plus 0.717 percentage of 4.16 turns out to be 0.035 now, 0.04 this time around. Next, 0.1 over 70.9 times 100. Again, now because you guys now have the hang of this, I'm doing this all on my calculator now. So this percentage that I got just from H plus 0.717, then I take this percentage of 4.33, turns out to be 0.037. Again, this will be rounded up to 0.04. 0.1 over 73.3 times 100 plus 0.717 percentage of 4.48, 0.038, again 0.04 plus minus 0.1 over 76.1 times 100 plus 0.717 percentage of 4.65 turns out to be 0.039, which is also 0.04. So any questions on how I filled up the table? How I got the uncertainties? Anything regarding this? All right. So now we go on to plotting this graph. So I have V in 10 to the negative 5 on my Y, theta in degrees Celsius on my X, and now I have to plot this graph. The nice thing about A levels is you do not have to, the nice thing about A2 is that you do not have to choose your scales. It's already been done for you. So I just need to plot these values now. So theta being 23 leads to V as 3.81. So 23 and 3.81. Also note here, this is not 0, 0. So this is a false origin. If you feel like you are a forgetful person, do write this down so that you remember that your y-intercept will not come from wherever this line cuts the y-axis, right? This is not a real origin. This is a false origin. So theta being 23 leads to V being 3.81. So 23 and 3.81. Let's zoom in here. So obviously this would be 23, 3.81. So these scales seem pretty nice to work with. All right. I'm making this blobbed intentionally here because otherwise the screens seem very, on the screen, these points seem very small. But do keep in mind that if you do make a blob which is larger than half a small square, like this, you will lose a mark, right? So this is one of the marking criteria as well. And there's also plus or minus 0.03. So on this axis, each box is 0.01. So 3 above and below. So 1, 2, 3. I make it like this. Make this slightly 1, 2, 3. And then similarly, the lower error bar, which is going to be 3 boxes down. So 1, 2, 3. And then I draw a small circle around this point. And then I join these in this way. All right, so this is how my error bar looks. Now to speed this up, I can obviously do this, you guys can't, is that I'm going to copy this error bar. In fact, let's copy all of this. So my new point then is 35 and 3.99. So let's go here. And it also has the same error bar. So 35 and 3.99. I think about this. This would be right here, right? 35 and 3.99. And it has the same uncertainty, 0.03. So it has the same error bar shape. Now, in the next ones, the error bar shape is going to change. So 48 and 4.16. 48. So this is 48, right? So this line is 50 and 4.18, right? So this is my point. And now because this is plus minus 0.04, so I go 4 above and below. So 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. And again the circle, right? Again, because I know that now my error bar is going to be the same, I'll just do the same thing here. So then my next value, I think I've done the first three. So 4.33, 62 and 4.33, 62 and 4.33. The 62, 4.33 would be here, right? 4.31, 32, 33, and this is 62. Next one is 73 and 4.48. So this is where I keep this one. And just the last point is left now, which is 88 and 4.65. 88 and 4.65. Which is this? Right, so now I have all of my points plotted. Just do a quick count to make sure that you did plot all of them. So you have all the 6 points plotted now. Now you also know what the next steps are, which is to draw the line of best fit, the line of worst fit. Line of best fit I'm doing using red, line of worst fit I'll do with blue. Again, when you are doing this in a paper, you will be using a transparent plastic ruler. But here, obviously, I have to do some sort of trial and error. So this is obviously not a good line of best fit. It leaves a lot of points above and not many below. I think this is probably better. So let's see. So one below, one above, on, above, and below. So this seems kind of nice. See if I can still make this somewhat better. Yeah. Now this is really nice. Both of these seem to be lying almost on the line. This one is below and this one is above, and they almost seem to be pretty symmetric in the amounts by which they're above and below. Similarly, this one and this one, they also seem to be the same amounts above and below. So I label this as my line of best fit, the one in red. And now for the line of worst fit. The line of worst fit, you guys obviously know it's much more easier to make. I, for some reason, always end up making the steepest line of best fit, but there is no such rule. You can also make the shallowest line of best fit if that is what you like to work with. Again, for the steepest line, I take it through the top of the first error bar. Make this a bit more precise. So let's do this using a thinner pencil. So top of that error bar, I'll also zoom in for a while, and bottom of the last error bar. But the requirement is that it must be passing through every error bar in between. If you look at the point which is second from the left, it is not going through that error bar. So I must shift my line so that it goes through that error bar. So now this is fine because it goes through every error bar. So it goes through here as well. and it goes through every other error bar. This is what it was previously not passing through if I do manage to make it pass through here, which is wrong. This is where you would lose marks. So the line in blue is my line of Weierstrass. Now, even without reading the question, you know what the next part is going to be, just to find the gradient and the uncertainty in the gradient. So for the best fit line, let's look at some points we can take. One really sweet point is this one. Let's try to read off what value this is. So this is 90 comma 4.7. 90 comma 4.7 for the best fit. Best fit. And I need another one now. Again, you guys also know another criteria for calculating the gradient is that the length of the is that the distance between the points must be greater than half the length of the line. So now I'm looking for a point closer to the bottom. Again, a really nice point, which is 20 comma 3.78. So 20 comma 3.78. Then I just use change in y over change in x. So 4.7 minus 3.78 over over 90 minus 20. Again, when calculating the gradients, also make sure what prefixes you had basically on both of your axes. This was 10 to the negative 5. This is pretty good to go. So your gradient is also going to be in a multiple of 10 to the negative 5, right? So before I forget, I'm going to write it like this. There will also absolutely be the absolute uncertainty, and there's all of this in 10 to the negative 5. So let's calculate this. 4.7 minus 3.78 over 70 turns out to be 0.01314. 3SF, I'm writing this as 3SF as well. Now I do the same for the line of Weierstrass. For the line of Weierstrass, obviously the choice of the points is also really easy because you take this error bar here, which it goes through. Also, this error bar you can confirm from your readings as well. For the last reading, you know this would be 4.65 plus 0.04. So this would be 4.69 and 88 comma 4.69. And that is also what you see here. So this one is 88 comma 4.69. And another one, again, you can take the other error bar you made the line pass through, which is this one. Right, so this is 35 and this is 35 and 3.96. 35 and 3.96. So the gradient, again, change in y over change in x. So 4.69 minus 3.96 over 88 minus 35. Now, because you did draw the steepest line, you would also expect that your gradient is more here. This is like pretty basic common knowledge that you can use at any stage to see if you have been doing it correctly or not. So this does turn out to be greater. This is 0.01377, so 0.0138. So my answer would be 0.0131 plus or minus the difference between the two. So the difference between the two is 0.0007. 0.00 and another one 7. It's up to you if you guys want to play by the rules and write it in a exact standard form. I really don't care for it that much right now. So I'm just letting it be, right? So this is what I get here. So yes, all right. Next thing is going to be obviously the y-intercept. And again, you know that we cannot use the intercept from the graph here. So for the best fit line, I just rearrange the y equals to mx plus c. So c would be y minus mx. So y minus mx now. So I just pick up a point. I pick up the gradient for the line of best fit. The gradient was 0.0131. And I pick up a point. So what was my y here? So let's do 4.7 and 90. So 4.7 is my y minus the gradient, which was 0.0131 times the 90, right? That's what I was getting. Let's just go up and confirm. Yeah, 4.7 minus 90 times 0.0131. So let's calculate this. 4.7 minus 90 and 0.0131 turns out to be 3.521. So 3.52. And I do the same for the verse fit. Again, c equals y minus mx. That gradient was 0.0134, right? 8, not 4, 8. And now I just need to pick up my y and x values. So y value, let's do this 3.96 and 35. So y is 3.96, x is 35. Let's do this then. 3.96 minus 0.0138 times 35 turns out to be 3.477. So 3.48. Again, writing my answer, it's the y-intercept of the line of best fit plus the difference between the two, which you can see here is 0.04. So now this stuff is done. So use your answers to A, C1 and A, C3 and C4 to determine the values of Y and Z, include appropriate units. Now, again, do make sure that you are playing around with the units correctly. Also do see here that in this case, the y-intercept would also have a 10 to the negative 5 here, right? This is the first thing you need to see, that your y-intercept would also have a 10 to the negative 5, right? Because this gradient also had a 10 to the negative 5. If I look here. So this would also have a 10 to the negative 5, and your y values also have that, right? So if I write it out like this, you would see it's okay. So yeah, if I wrote it out like this, 10 to the negative 5 minus this, which is also 10 to the negative 5. So let's see. Right, so this is also 3.52 into 10 to the negative 5. It's the same thing, so don't forget this here either, right? This is important stuff to keep in mind, otherwise all of your answers get messed up. So now you need to use the gradient and the y-intercept expressions to, again, go ahead with this. Let's take a screenshot of what we just wrote down here. All right. So the gradient is yk over p. I need y from here. So y would be what? So y is gradient times p over k, all of which is given. So the value is not really difficult to calculate. I want to talk more about the units part. So the gradient I had as 0.0131. This is 10 to the negative 5. This is 10 to the 5, so they would cancel out anyway. So I have this 1.01 here really, and divided by k, which does have some prefixes, which is 1.38 into 10 to the negative 23. So let's find this out, what this is. 0.0131 times 1.01 over 1.38 into 10 to the negative 23. This value turns out to be 9.587. So you can also take this as 9.59 into 10 to the 20. Now, how about the units? So if you think about what the units of the gradient were, so the units of the gradient are always units of y divided by units of x. So these were really meter cube per degree Celsius, right? So this is, where do I write? All right, let's take this here. So this is in the numerator meter cube per degree Celsius, and 1.01, this is just pascals, and this is divided by joules per Kelvin. Now you know that joules per Kelvin or joules per degree Celsius, these are really the same things here, right? Why are these the same things? Because temperature difference is the same if you talk about the Celsius or the Kelvin scale. Now, when figuring out the units, this is where the entire initial part, which we skipped through initially, that is going to help you out here. Because that always talks about what y really is. So let's go back to this question. So if we read here, so you're given what h was, k is, all of this stuff. Right? So if we go back here, y, so this is meter cube times pascals. Let's think about this for a moment. So meter cubes times Pascal, if I go into a little bit of units analysis here, so meter cube and your Pascals are really the units Newton per meter, right? Force over area. So this becomes Newton meter squared, right? So you can see that this is Newton meter squared, which is also the same thing as the joule. No? Work and Newton meter squared, these are the same thing. So what this becomes, sorry, this should have been meters squared. And what is left here is just a meter. Redo this. Because this is force over area, so Newton per meter squared, there's the meter cube. So it only leaves out a single meter. So Newton meter, right? Work, force times distance. This is the same thing as the joule. So this has no units here. Nothing. All right. So the units analysis is slightly tricky here. If you feel like you are getting stuck with it a lot, honestly, it's not worth it. It's just 1 mark. Go ahead and then come back to it later if you have the time. All right. So you do this. And now you go on to Z here. So units for Z is y-intercept times P. Also, you guys can see here that yk over P is just the gradient. So you can also say y-intercept is the gradient times Z. Y-intercept is gradient times Z. So Z is y-intercept over the gradient. Again, I don't have to worry about 10 to the negative 5 because that is the same in both places. So y-intercept was 3.52 and the gradient was 0.0131, right? So 3.52 over 0.0131 turns out to be 268.7. So 269. Again, what are the units of this going to be? Because this was the y-intercept. Y-intercept just has units of whatever you have on the y-axis, which is meter cube. And the gradient is units of y over units of x. So meter cube per degree Celsius, right? Meter cubes cancel. So the units for this are just degrees Celsius. Guys, let me know if you have any problems with understanding how the units come about. I'll be more than happy to explain. All right. Determine the percentage uncertainty in Y. All right, I see we have a question. Can you explain the units for Y? Sure. Look, for Y was the gradient times P over K. If I just, first of all, let me tidy this out again and do this again so that it makes more sense to you. So as I just wrote down, for Z, the units of the gradient are units of Y over units of X, which is meter cube per degree Celsius, right? Units for P are given as pascals. So this is pascals. And units for K are given as joules per Kelvin. So right now I feel like all the units are like all over the place. But you know that from your ideal gases knowledge that you have, you know that degree Celsius and Kelvin are the same when talking about temperature differences, because temperature differences are the same in that, right? Now what I have left is meter cubes times the Pascal. For the Pascal, I know Pascal is the unit of pressure, which is force over area. So this is force, which is newtons, over area, which is meter square. So the meters cancel out like this, that I have just a meter in the numerator, and here I have joules. So on the top, I have Newton meter. And if you think about it, this is the units of work. This is the formula for work. Force in Newton, distance in meters, which you know is also joules. So ultimately, all of these units cancel out. This, all of these cancel out, and Y has no units. All right. This is how we reach this idea. I know it's a bit tricky, but give it some time, let it grow on you, and you'll probably understand. Sometimes for these units, you do have some hints written here. Like sometimes you know what these constants are. Here you have no idea what these constants are, right? You don't know what Y is, you don't know what Z is. Sometimes you do know them. For example, if you look at the March 24 paper, there you had to find some unknown values as well. They were Z and Y. But in the pretext of that question, it was written that these are resistances. So at the end of the day, I also know that they are supposed to be in ohms. All right. Percentage uncertainty in Y, if you look at the formula, so I can say this is going to be the percentage uncertainty in Y is going to be the percentage uncertainty in the gradient plus the percentage uncertainty in P, right? K is a constant, so no percentage uncertainty here. So for the gradient, now I need to go up and see what these values were. So 0.307 0.307 over 0.0131 times 100. But again, because I also have to do the same for P, I'll do the times 100 later altogether. So this is 0.01 over 1.01. And this is my percentage uncertainty. 0.0007 over 0.0131 plus 0.01 over 1.01 times 100. So this turns out to be 6.33 or 6.3%. All right. The experiment is repeated. Determine the temperature theta that gives a value of H of 60 mm. Now for this last part, you have a choice in terms of what you want to use. You can choose to use this linearized equation that you had, or you can also just choose to work with whatever the examiner had given you. So let's take this to go as well. So we need theta here. It's up to you if you guys want to first make theta the subject and then plug in values. I personally find it a lot more cleaner to make theta the subject first. So if you see here, theta would be PV over YK minus Z. This is all the working that you need to show. Once you have written this, now you just go on to do this actually in terms of the values, and then you just give your final answer. So PV, P was given as this value here, right? So 1.01 into 10 to the 5. Let's actually do this here because I know it's going to get messy. 1.01 into 10 to the 5. What was V? Oh, so H is given. So we need to find V again using this formula, right? So pi d square H over 4 pi so again D was also given to us, right? So we also have D. So this 27.9. Again, let's keep everything in SI units. Let's keep all the prefixes. Let's convert all the prefixes and then let's see what happens. So pi d squared, so 27.9 into 10 to the negative 3 squared. H is 60 mm, so pi d square H. And this is also over 4, right? This is just the numerator, by the way. And then you divide by yk. So y and k now. Let's take this here now that we know how this works. And yeah, so y is 9.59 into 10 to the 20. K is the Boltzmann constant, 1.38 into 10 to the negative 23. And from this you subtract Z. And from this you subtract this 269. So let's do this all in a calculator now. 1.01 into 10 to the 5, 2 pi. Minus the Z, 269. So this turns out to be 10.94. So I can write this as 10.9. Again, in keeping with all that I've written in 3SF. All right, I see we have question. Should I remember the formula for theta? What formula? The one that I just got rid of? Is that what you're asking? What formula are we talking about here? Abdullah, what are you talking about? The one we used a few questions back. Uh, Honestly, I can't seem to understand what you are talking about. Which formula for theta? Guys, can anybody explain if they understand what Abdullah is trying to say? He's saying, should I remember the formula for theta? I don't think we. I mean, I just linearized it. I just did simple algebra. If this is what you're asking, let me go back up here. From this, and absolutely no, you should not remember theta. You should not remember theta. I made it the subject from this equation because theta is what the examiner was asking of me, right? If maybe it was asking me for P given everything else, so I would make P the subject, right? So why would I wouldn't have to memorize it. You have to memorize nothing in P5, especially in question number 2, except for like rules regarding how you make the table and whatnot. Otherwise, yeah, this is how it goes. Guys, any questions about making the table, calculating best fit, worst fit, gradients, y-intercepts? All right. So, because you guys are in the thick of your papers right now, no homework. Next time we'll be doing Winter 2352, and of May, on the 12th of May, we are going to have our AMA session, which is going to be accompanied by the guest paper and somewhat good questions that I feel like have a chance of making an appearance in your paper. So that is going to happen. Let's see, what time did I decide on? What time? We decided on 4:30 to 6. Right? That's the time we are going to give for our live AMA session. Do I need a somewhat extensive knowledge of P4 content for P5? Not really, but it always helps. Like for example, if you have a question in which you have to measure the magnetic flux density, then knowledge of the Hall probe helps. For example, that you know that you should rotate the Hall probe until you get the max reading, or how you should place the Hall probe so that its plane is perpendicular to the coil, for example. So yeah, it does come in handy. A lot of the times you can use it to double check stuff, but you don't really need it, technically speaking. All right, guys. So let's call it a day here. Then let's meet inshallah on day after tomorrow. Right? I think that's when we meet next. Yeah, same time, 7:30 to 9. And we'll be doing the other P5. Take care, guys. Best of luck. Last question. How do you suggest we prepare for P5 the day before the exam? Honestly, if you, I mean, for P5s, as a student and as a teacher, I feel like question one is what you can really prepare for. Question number two is just a matter of practice. The more you do it, the more you figure out what the different type of questions could be, like for example with units and stuff. But otherwise, it's just something you either know or you don't, right? For question number two. For question number one, what you can do is like you can go through examiner reports and mark schemes, and you can see that for certain types of experiments, what was asked, and what was like theme, as to like some different additional details required, that you can get from the examiner report and the mark scheme. For example, like this one that we did here. All right, I shared it off. Let me share again. So like for this question number one that we did, you had a question on oscilloscope, right? So for oscilloscope, you can always write about the time base and how you use the time base to find the time period and how you reciprocal it to find the uh, frequency. And similarly for the Y gain. So if you think about it, just talking about the oscilloscope here gave me like 3 to 4 marks out of this entire 15, just on additional detail I'm talking about, right? So yeah, the more you know about what you have to write when using certain types of apparatus, then you can always do that, right? So reading the examiner report always comes in handy. All right, Abdullah, does it make sense? Okay. Best of luck, guys. So let's meet inshallah day after tomorrow on 11th, same time, 7:30 to 9. Take care. Bye bye.